Okay. Welcome again. Today we'll talk about implementing CPA-secure, so chosen plain text attack, secure encryption, using block ciphers modeled as pseudorandom permutations. We introduced these concepts last time, but let's start by reviewing them quickly. Here is the notion of CPA security. Adversary, so let me just bring the whole thing, right? So you have a cipher, an encryption, decryption, key space, message space, ciphertext space. And as in the case of indistinguishability, you have a secret bit and a key is chosen. Now, faced with such a system that chooses a random key and has some secret bit, adversary can do the following. He can specify any message and get an encryption under this key for that message. This is called plain text, chosen plain text attack. He chooses the plain text that he will see an encryption of. Then at some point, there is two messages that are challenge messages. As in the notion of indistinguishability, adversary chooses what they are. And he gets to see an encryption of one of them. Which one? Chosen by the secret bit. Then he still, after seeing the ciphertext, he might continue making chosen plain text attacks. In particular, these messages could be related to these. They also can be related to the ciphertext. And he gets an encryption of whatever he wants. Only then he has to decide the bit. And as before, advantage is defined as a correlation between this bit being 1 and this bit being 1 versus this bit being 1 and this one being 0. Okay, so this is a generalization of indistinguishability. Namely, if you just take away this part and this part, you get indistinguishability of encryption, right? Okay. And we have seen that any deterministic encryption scheme like stream cipher or one-time path would fail this notion, okay? Because the ciphertext are deterministic function of plain text, so the minute one of them is equal to these challenge messages, you can just detect whether this resulting ciphertext is the same as this one. So deterministic encryption cannot do it. Now, what are the block ciphers? We'll model block ciphers as pseudorandom functions or pseudorandom permutations. We had the switching lemma that shows that asymptotically these two modelings are equivalent. What are those? Okay, again, as before, there is a secret bit. At this time, this bit will determine whether the box adversary interacts with is a block cipher. Okay, so PRF, namely that the random PRF key is chosen and the function that interacts with is chosen as the PRF with this key, or this is a completely random function that is independent of the code of F. Okay, so think of F as a block cipher, and here is the capital F, and the little f here is a random function. Here it is a block cipher with some chosen key. An attacker will can send any plain text blocks and get back this function operated on them, right? And if this function is a PRF, then these values all look like this is fk on x1, this is fk on x2, this is fk on xq. All of them have the same key k. The same key k acts on them. So that's what you see in the real world, which is B0. The B1 models the ideal world where we replace this function by an idealized function, just like when we define PRG, we replace the PRG output with idealized notion that We would like it to be just like a completely random string. It is not. It is output by a small circuitry on a random seed, but a small seed, right? It's not a random string, but we, in the ideal world, we treat it like a random string. The security is that the real, which is a PRG applied to a seed, and the ideal, a completely random string, you cannot tell. No efficient algorithm can tell. Therefore, for all practical purposes, PRG outputs look like random strings. Same here. In the real world, you will be interacting with an AES instantiated with some key, random key, and you will get to see outputs of the real AES on this consistently same key, but any plaintext you like. In the ideal world, you will replace that by a complete random function to just assign random values to each argument. And the PRF is secure if, again, there is no correlation between these two bits, except from negligible, right? So it's the same type of notion. And the only difference between PRF and a PRP, in some sense, is like it's right here. So that instead, in the ideal world, we don't consider this as a random function. We instead consider this a random permutation. Okay, most of the time it would not matter. So now, okay, that we recall these notions, we're ready to let's use block ciphers to encrypt and to achieve security against CPA security. Let's look at first very common, it's like a knee-jerk way of using a block cipher, which will be insecure against CPA security. Is in fact not even indistinguishable. And then we'll see how to really do it. Here is called the mode of operation of block cipher, which is called an electronic code book mode. By mode of operation of the block cipher, the block cipher is what it is. It always operates the same way. It has some circuitry, it has a key, and whatever plaintext you give, it has a code and output ciphertext. The point is, it operates on short blocks. It always gets AES. You can put in only 128 bits into it. For DES, triple DES, you only input 64 bits. The mode of operation of a block cipher refers to how do you use a block cipher to encrypt larger messages. And here is a knee-jerk way to do so. If you have a long message, just divide it into blocks which are equal in size to the block size of this block cipher. We'll model the block cipher as a PRP, pseudo-random permutation. So in the case of AES, each of these blocks is 128 bits. In the case of DES, triple DES, 64 bits. Okay, and just for each block, run the block cipher, PRP, on its key and feed the blocks into it. And the ciphertext, the blocks that PRP outputs, concatenate them, and that's your ciphertext. So this is not even indistinguishable, because if this MI here is not different messages, the plain text is the whole thing divided into blocks. So this M1 and M2 are two different blocks of the same message. And the problem with this is that if the plaintext contained two blocks which divided into block size were identical, then the corresponding blocks in the ciphertext will be identical as well, right? Because this is a deterministic procedure. So if you feed it the same input, it's going to give you the same output. Okay? And this means that it's not even indistinguishable. So here is an AES encryption of a photograph. When the all black string, right, it's encoded as either all zeros or all ones, whatever that was, okay, the cipher of that is some 64 bits or 128 in this case of AES. These 128 bits encode somehow but every occurrence of the same string here will create the same string on the in the in the cipher. So this does not look random, and basically if you send a photograph of a dog, it's not going to have this outline. So you can basically tell a ciphertext that encrypts. Perhaps you cannot tell this guy, but you can tell a dog from a human, from a cow. So it's not, so that's a violation of indistinguishability, right? Because the cipher has to be indistinguishable no matter what M1, M2 is. If M1 is a picture of this guy and M2 is a picture of a dog, you don't need a sophisticated algorithm to distinguish between their ciphertexts. And here it is formally, right? So indistinguishability one-time key. So indistinguishability refers to attacks on just, oh, somebody has some other example. Yes, go ahead, look. I'm not gonna do now, but so you can post it on Piazza for people who don't who are not right now on the cannot see that chat. Okay, thank you for that. Okay, so the one-time usage of the key is that there is two messages. In this case, think of M0 as a picture of this guy and M1 as a picture of a dog. And you either get a ciphertext encrypted guy or encrypted dog picture, right? And this should be negligible, but it is not. Right, and here is the simple attack. Basically, the attack was when there were two blocks that were the same in one picture. So we recognize this pattern in the ciphertext, or they were different, okay, in the other picture. So here is the most basic example. Consider two messages that have only two blocks each. They need to have the same sizes, right? So the two challenge messages have to be equal sized. Otherwise, it's not a fair attack. So think of M0 having the same two blocks and M1 having two different blocks. You get an encryption of MB, which is either that or this. But now, if you know that somebody used electronic code book to encrypt, then this block will be an encryption of this block and this block of this in case of M0, but in case of M1, both of these blocks will be encryptions of the same block, hello, hello. So these two ciphertexts will be the same, right? So if you use ECB, then this is the encryption, right? It's the block cipher, PRP. C1 is PRP applied to the first block of message MB, right? So either M0 or M1. And C2 is the second block. So it's the permutation, PRP, with this key applied to the second block of the MB message. And so if bit is 0, then these two blocks are different. If bit is 1, then these two blocks are the same. So this is your decision procedure, and it gets you fantastic in the distinguishability, right? So the difference is basically 1, because it's a PRP, not a PRF, meaning it has no collisions. So if these two blocks are different, then an output of the PRP is also different, right? Because PRP is a permutation, it doesn't have collisions. So you will never encounter this case in case you're encrypting M0. And you will always encounter it if you encrypt M1. So distinguishability cannot be better. Okay, so let's, here is now how you can encrypt long messages with a PRP. Actually, let's switch and think of this as a PRF. is going to be easier. And okay. So let's now pretend that this, not pretend, but just assume that the block cipher is a PRF. And encrypt long messages in this way. Divide it into blocks like before, but don't feed these blocks into the cipher, into the PRP or PRF in this case, into the block cipher. No, feed constants feed consecutive counters into the into the block cipher. Okay, namely compute the block cipher on plain text block all zeros. So these have to be encoded as in appropriate sizes, right? Like if this is a yes, the 0 stands for a string of 128 bits that encodes 0. This 1 here stands for 128-bit string that encodes 1, etc. But we can encode into arbitrary lengths, so that's okay, right? So you're running a block cipher on these inputs, and then what you do with your message blocks, you XOR the block cipher output with the message. Now, to decrypt, you run the same procedure with ciphertext and plaintext switched, right? So the decryptor puts the ciphertext here, computes these PRF outputs as on this picture, and XORs them, right? And basically, it's a form of a stream cipher. So in order to encrypt a message, I took my key and I expanded it into this long string. This string is actually a PRG. And we will come back to this. So this is basically a case of a stream cipher that you've already seen before, but with a PRG implemented using a block cipher in a counter mode. That's called counter mode operation of a block cipher. You take a block cipher and you feed it counters, consecutive counters, and you just watch what it creates and you gather what it creates. Here is the statement about this counter mode. We have any attacker against the counter mode, indistinguishability of a counter mode, it has basically the same advantage, away by constant 2, from the best attack against the PRF property of this block cipher. And that means that if you believe it's a secure block cipher, so therefore this is negligible, then so must this be, which means that this encryption mode is secure, as indistinguishability. Here is the proof by pictures. Basically, this is nothing new, because what are we going to do? If the challenger encrypts M0, what we get as a cipher, the ciphertext that this attacker gets is an XOR between M0 and all these consecutive values of the block cipher output. In this case, it gets to see M1 XORed with this consecutive block cipher output. If PRF is secure, then by exactly the same reduction that we did in the case of block cipher construction, where this line here was a PRG, PRG output on a key K, if there is a distinguisher between PRF outputs on constant 0, 1, 2, 3, L, then there would have to be, sorry, take it, let me say it this way. If there is a distinguisher between this type of ciphertext and this type of ciphertext, where here I replace this PRF with a true random function, and these cipher blocks are M0 XORed with consecutive output of this real random function on consecutive integers. If there is anyone who could see this view from this view, then the same simple reduction we did earlier would show that you will have to distinguish between these and these, and the reduction would. And we know by PRF security that you cannot distinguish between these and these, except for negligible advantage, because it's a particular case of an attacker against the PRF. It's an attacker that just happens to send, I want to see the PRF output at point 0. So x1 is 0, x0 is 0. I want to see another output on x1 equal to 1, and then on x2 equal to 2. These are particular input strings. They are consecutive counters. If the attacker talks to a PRF, he will be getting these blocks, and he can concatenate them and form this row. And if he talks to a random function, then he will be getting these blocks. The assumption that PRF is secure is that no such attack can distinguish real PRF from a random function. Therefore, in particular, he cannot distinguish them if he queries this cipher block, this cipher on consecutive integers. Okay, so now recognize that because it's this is a random function, this is a completely random string, because a random function on consecutive integers, or in fact on any L plus 1 distinct arguments, its outputs of a random function are just random strings, and they are uncorrelated. That's the notion of a random function. On any arguments, it just gives you random values. So this is a collection of L plus 1 independently chosen uniform bit strings. Therefore, this whole thing is a random string, and therefore by a one-time pad argument, there is no difference between XORing M0 with random function outputs and M1 with random function outputs. And of course, we complete the picture here by the same argument we did here. So another way to look at this, and we conclude that therefore these two are indistinguishable. So this is a secure indistinguishable encryption. Another way to do this is to recognize that if you collect PRF output on consecutive integers, or in fact on any constants, distinct constants or arguments really, then that forms a PRG. And so if you have a block cipher, then if you have a PRF, then you have a very easy construction of a PRG. Just run a PRF on any distinct constants as long as you want, because polynomial time. So if the input blocks, if the block size is polynomial in security parameter, then I can fit exponentially many different constants, right? So any polynomial I want, I can still fit it as in the block, in the input plaintext block, in the input to a PRF. Okay, because it has a sufficiently long domain. And by the PRF property, all of this is indistinguishable from a random function applied to these distinct indices, and therefore it's indistinguishable from a one big random string, right? So once you recognize that, then the deterministic counter mode is just a case of a string cipher. Okay. Okay. So this is we did. Okay. So here is an example. But word of caution, deterministic counter mode, as the name suggests, is deterministic. There is no randomness here, right? If I have a key and a message, I have a deterministic procedure here. So if I run, this was a way to encrypt arbitrarily long messages, but it's still just encrypting them only once, because any multi-message security notion, like CPA security, this will fail, right? Because it's deterministic, so it will fail it. Like, even if you can ask two things, then having seen an encryption of a long message, now you will notice it repeats. Whenever it repeats, you will notice. So here is an example of a randomized encryption, which just takes this deterministic counter mode and twists it very, very small amount. Let's consider a PRF. I'm going to now treat the input size of a PRF as the randomness domain of the encryption. And the output of a PRF will be my message space of an encryption. So if F is a block cipher, then R and M are the same spaces. Right, for this is 64 bit strings, and this is 64 bit strings. But it works for any PRF, which has different domain and range. So here's how I encrypt messages in this space. This is a randomized encryption. I choose a random element from the domain of the PRF, and the ciphertext is a pair of values, encoded by concatenating the first element to the second, right? Because they have fixed sizes, so it's unambiguous. First element of the ciphertext is an R, this randomness. So in the case of DES, it would be 64 bits. The second element is an application of the cipher on this randomness, XORed with M. So this is like the deterministic counter mode that you just saw, but rather than using consecutive integers, I'm losing my pointer. Sorry. Rather than using consecutive integers, I am using a random integer. And because I'm encrypting, but it only works for encrypting short message. The message has to be as big as the output block size of the PRF. Do you want to vote whether it is secure against the CPA notion? So is this secure against a CPA attack? In a CPA attack, adversary could choose a bunch of messages, get to see their encryptions, and who can do it polynomially many times. And then there is some challenge message, M0, M1 pair. He gets to see an encryption of MB, and then he can continue CPA attack. So he can send new messages and he gets back these pairs. Every time, notice, key K stays the same throughout this operation, throughout this experiment, right? Because the whole point of this is to model multiple usage of the key, of the same key. But every time the attacker asks for an encryption of something, new fresh R is going to be chosen, and what he gets is R, comma, his message, XORed with FKO at R. So any Any guesses as to, which is the proper answer? Yes, the whole thing is about collisions. So it is secure when F is a PRF, except for one problem. So if F is PRF, then these outputs are indistinguishable from random outputs of a random function on R's. So far so good. So therefore, you can use them to XOR, and by basically one-time pad security argument, the randomness in this function obliterates the XOR, obliterates any information in M. But that argument has one little problem. What if the little r's ever collides? So if little r ever collides, meaning I'm talking to this encryption box polynomially many times, right? I can ask him Q queries, and Q is some polynomial in the security parameter. Every time he's going to pick a new R, so R1, and I get to see FK of R1, XOR M, but because I chose M, I basically get to see FK of R, right? Because this is chosen plain set attack. So I send an M and I get back M XORed with FK of R1. Of course, I learn FK of R1 from that. Next message I encrypt, I get FK of R2 by the same thing. Then on a challenge message, some R challenge is chosen, call it R star. And my message M0 or M1 is encrypted as XORed with FK of R star. If R star is different from all these RIs, then I'm cool, because if it's different, so it's like a random function on a completely new argument, so it's a fresh one-time pad. But if there is a collision between R star and any other of the RIs, then I win, because it's basically a repeated usage of a one-time pad, right? That was now used twice, and I basically know the one-time pad already because it's chosen plain an attack gives it to me. So I just XOR it out, and I know whether you encrypted M0 or M1. Right? So this is the proof sketch that is here, right? In the argument, I will first step, I will say, if an attacker succeeds in this, then whatever probability he has with 1, it's with indistinguishable probability that he still outputs 1 when I replace all FK executions with the random function executions. Or otherwise, I can build a reduction that replaces talking to FK, that distinguishes talking to FK and talking to a random function. This reduction, it sort of follows from the reductions that we have seen. And you can also build it explicitly, if you like, and we can do this on a sheet of paper. But okay, so let's say you believe in this reduction, right? So in this move from the blue world, which is the real world, to the sort of idealized world where we replace the PRF with a true random function. And now the only thing is collisions in R's, right? So it has to be that the block size is large enough for this never to repeat. And this is also why block size matters, right? Sorry, this coincidentally, now that I said it, like block size matters, it resembles some other thing, obviously. Okay. If the block is not large enough, collisions will occur, right? And that's basically the same thing that we have seen with the switching lemma. The birthday probability. Now, if your block size is small, okay, so say that you have a router, okay, that is going to, you don't want to change keys all the time. You want to have the key and make it last at least for a day. You say, estimate your traffic, and you say, okay, I'm going to send, 1 billion messages, IP packets at most. Okay, so 2 to the 30. Okay, now if you have a 64-bit block of DES, what's the probability that any of these arrays that you will pick when you encrypt this way will collide? So same key, and right, if you had 2 to the 32 messages, well, then the approximation to the probability with which it will collide is unfortunately square of the number of samples divided by the size, of the set from which you're sampling. So it's 2 to the 32 square, which is 264, divided by 264, and that's not a great bound because it's 1. Yeah, so basically you shouldn't use it, because it will be very likely that you will encounter a collision on these arrays. Okay, but you can say, well, let's just do it differently. Let's not pick arrays at random. Let's do a counter mode, deterministic counter mode. So initially the R is 0, and every time I run it, I increment R. Now I'm guaranteed no collisions for 2 to the 64. And 2 to the 64 is a lot, so I'm good. The problem in practice with this design is that it's stateful. There's two basic problems. It's stateful. So now it has to remember. It has to not only read key, right, which doesn't read because it's just in the, it's in the volatile memory. But it has to write. It has to keep this constant state, right? So, and then there is glitches. There is basically, it's insecure against reset. So in case there was a glitch and you needed to reset, you will be completely insecure. So people don't like deterministic counter modes, and as designs that is secure with a randomized, without a keeping state is preferable. Okay, this will actually come up as modes of operation of a block cipher. So let's look at this. Basically, what we have seen here is a randomized counter mode. And you can say, you know what, maybe one thing I should say. So this is CPA-secure. We already argued that. Why not encrypt long? But the problem with this is that it encrypts short blocks. Let's say that F is a AES. So these are 128-bit blocks. So you can only encrypt 128 bits this way. Okay, so if you have a long message, you're going to divide it into 128-bit blocks and use this to encrypt each block separately. That works. It's a particular case of a using of a multiple usage encryption, right? However, it's awfully inefficient bandwidth-wise, because every 128-bit blocks will be encrypted as 128 bits here and 128 bits here. So you basically, ciphertext is going to be twice plain text. That's bad. Like, like if I download a song, whatever, like 5 megabytes, but now if it's encrypted, it takes 10. Nobody would want that. Basically, a factor of 2 cost of encryption in bandwidth is not acceptable. But here's a simple hack, if you will. If you have long message, pick a single randomness and combine a randomized counter mode with the deterministic counter mode in the following way. The random IV, this is the R from the previous slide, is chosen to encrypt. Let's say that the PRF goes from n bits to n bits. So each of these blocks is n bit long. I parse my message into L n bit blocks. I choose this random n bit string. And then what I do is that I compute the PRF on the string incremented by a counter corresponding to the block, which block I'm encrypting. So, there's elements of the counter mode here, right? I take an increment, I just increment this counter, but this counter doesn't have to be permanently stored. Like when I'm done with this message, I forget about this, and the next message comes, I choose a new IV, and I rerun this, okay, on basically new arguments. My ciphertext is the randomness and the XOR between these and these, right? And the decryption given the IV, it stands for initialization vector. It recomputes this this row and encrypt and XORs as before. Okay. Now this is very nice also because it's parallelizable, right? So if this is the long message and you have multiple cores, you can do separately. You can encrypt separately, and decryption has the same circuitry, so it applies to both of them. This is if F is a secure PRF, then if the block cipher is a secure PRF, then this is CPA-secure over any message space that takes. So the messages in the CPA encryption are sequences of L blocks, where the underlying blocks are the blocks of the block cipher. Ciphertexts are one block longer because they also include the IV. You actually can use it on variable size messages. This capital L does not have to be fixed. So it's fine to use the same key for any length. You can convince yourself this is true because, if it's true for fixed, then just pad with zeros, run it, and throw away the other blocks. And so therefore, it must be true about the substrings, which are the encryptions of the effectively shorter messages. But we assume that messages are, are parsed into these blocks, right? So if whatever any attacker against this, whatever advantage it has, it must be at most the inherent bound on security of the PRF. However, there is an added factor. This factor is Q square times the length of the number of blocks in messages divided by the block size. This Q square is because for the same argument, think of L being 1. So therefore, this is exactly the encryption I was telling you. Messages are short blocks. For every message, I get a new IV, and I just XOR FK of IV, well, +1, but that doesn't matter, with my message. So I definitely have the same Q square in the bound because that's the probability that there is a collision between IVs. But now it's multiplied by L, because if you think about this, it's all about what's the probability that this range of L consecutive numbers intersects with some other. So now instead of with the birthday bound, which is I have a space of randomness, and I sample from it, R1, R2, R5, R4, R5, R6, right? And what's the probability of them colliding? Now I generalize it. I have ranges of L starting from a random point. So I have my total range, and I throw in these L-sized ranges at random points. The probability they will intersect is q square of the number times the length, and that's not hard to see. So the proof again it will be, okay, change the fk with a true random function, and this basically takes care of this part. And now look at the probability that that the range of counters IV, starting from IV and ending at L, falls into the union of the previous counters. And rather than think of IV plus L, I just think of IV itself and generalize these ranges into IVI minus L to IVI plus L, right? It's simply, instead of thinking of this new range intersecting with the previous one, I extend and I just look at the counter, right? It must fall in here for there to be intersection between these two sets. And because it's a union bound, so basically it's 2L times Q squared. And that's right. So this you can see, say there was no bound, there's no collision yet. So the total size of this is 2L times Q. And so the probability that the new guy falls into something like this is 2QL divided by the size, but you do it, that's true for Q equal 1 and Q equal 2 and Q equal 3 and Q equal 4, right? So in the end, okay, what is it? Sorry. It's a sum over these type of terms for Q, so after K, this is 2KL, and I'm summing over K from 1 to Q. That's what I will get, right? Divided by 2, but that's a constant. Okay. And a practical implication of this is that, if I want, say, 1 billion probability that this will happen, that the attack will happen, if I have an AES who has 128-bit blocks, so the space from which I'm sampling randomness has this many elements, then take square root of both sides. So this will give you Q times L square root of L. And hold on a second. You know what? I have to kill things because I'm not seeing myself. Okay. So this is the bound on this expression, right? So in particular, this part must be smaller than this probability. And And so if this has it's a it's so so I move x to this side, right, and I get 2 to the 128 minus 32, and I take a square root of both sides. Then it gives me q square root of l smaller than what I had there, 2 to the minus 128 after this moved to the side, minus 32, but square root. So it's this. So this is 96, right? And half of that is 48. So this is the bound on how many messages I can encrypt and how long they are. Okay, so for example, if messages are basically no more than 4 billion blocks, then you can encrypt so many of them, and that's a huge number. So this will tell you where you should refresh the key. But if you do the same calculations for but the same actually, and a different so first, if we do this calculation for death, then it will be absolutely horrid, but also you will see another mode for which this bound will be worse. Okay, it's a cipher block chaining mode. When you see the circuitry of randomized counter mode, it seems a very natural thing to do, and it doesn't seem like how would you arrange the stuff differently? But this is also a natural construction, and it works like this. You use the IV, so where CBC came from. It's we knew that electronic code book, basically you take a message block and you just feed it directly into the cipher. So first erase these XORs from your view. Okay, this is as electronic code book mode. So people knew that, okay, this is bad. If you have any repeat in these message blocks, you're gonna have a repeat in the cipher blocks. So let's randomize it. How? Every time you encrypt, pick the random initial vector, and what you do with it is you randomize the plaintext block with it. So what you encrypt is not the original message, not the original block of the JPEG right that we saw as an example, but the block randomized, XORed with a random shift. So that's what you encrypt. Okay, so far so good. You randomize the first block. What do you use to randomize the second block? If you use this, then that would be dumb. You again, repeats in the blocks would imply repeats in this wire, right? If you XOR with the same IV. Okay, so next best thing. How about using the cipher? If this is a PRF, so outputs of it are like a random string, then you use this random string as a randomization of the next block. And so basically fix the ECB mode by randomizing the plaintext blocks using the initial fresh randomness, and then using cipher blocks as randomness for the next each next plaintext block. Okay, that's the design, and so it sort of comes out as a natural fix to the ECB. What Well, what is the decryption? I have some slide about it, but let's just walk through it. How do you decrypt? Let's say this block I want. Well, what I given a ciphertext, remember E is a block cipher. So there is a decryption circuit. I run the decryption circuit with key K on C2, I get this wire, and I need to now just XOR it with this cipher block to get this register. And it didn't matter that I did it here, right? Like to get back M3 is the same procedure. So this is the circuitry. And note I need to, now I really need this to be a PRP, not just a PRF. It was actually convenient for me if I looked at the analysis of this mode and I assumed that F is a PRP, I would have to deal with collisions in these outputs. And just thinking of this as a PRF allows me not to think about these possibilities, right? But here, I cannot think of this as a PRF. I mean, I could, as these are some place in the analysis, but it is a PRP, but I have to require this to be a PRP. I require that there must be a decryption circuit that inverts, the E function with the D function. The nice thing, though, is that this thing has parallel decryption, right? Because to decrypt this, all I needed is to look at these two. So I could split in the middle and have some circuitry decrypting these two and a separate circuitry decrypting these two. It's not true for encryption. So in order to encrypt, get that cipher, I did need this wire, and I needed this wire, and I needed this wire. So encryption is sequential in CBC. And it has a worse bound. So the analysis is the best we know of, is that, and okay, now I'm forgetting what is tight. So you see, in these results here, it is not just an upper bound. It is a tight upper bound. Namely, there actually exists an attack which will achieve this advantage, because simple throwing balls into the this randomized process of throwing the IVs into the bucket, and this just was sheer luck that there is a collision, and this collision happens exactly with this probability. So this is a tight relation. Here, I just don't remember right now whether this is a tight relation. So is there an explicit attack? I think so, actually. I should have checked that before the lecture. In any event, the best we can show is that this is bounded by Q square L square over the domain size. Analysis of CBC is more complex. It's just not as straightforward as the other algorithms. I mean, you can think that, no, I shouldn't say straightforward about the other algorithms either, but okay, it wasn't like such a hard analysis, really. This guy doesn't have as easy an analysis, and it's also for the reason that it is, well, anyway, so again, I'm not sure this is tight. I think it is, but the analysis only gets you this bound, and it is worse now, because if you plug the same numbers, So you put this on the right-hand side, right? You have 2 to the 128 minus 32 square root. You get 2 to the 48 on the right-hand side, and this q square L square becomes QL. So the number of messages times the number of blocks is 2 to the 48. And that is not so good. So this is already approaching what somebody could do, in a I don't know, a few weeks. So this basically means you can use this mode, but you have to refresh the key more often. I mean, in a high volume application, like a router of or a VPN for a organization, or like UCI. And when you instantiate with the when you instantiate it with DES, and this is now not 2 to the 128, but 2 to the 64, I move it on this side, I get 2 to the 32, right? 64 minus 32. Then I take a square root, and I get just 2 to the 16. And so basically, this is completely ridiculous, right? It's a very, very small amount. It makes no sense to just be able to encrypt so many blocks. So these things matter in practice. Here is you might think, and so look what happened. Regardless of the message size, I had this initial IV, yes, and then I reused the next cipher as a randomization for the next block. What if let's say my message was only M1 to M2, so it ended here, and this is where my ciphertext ended. If M3, M4 were not blocks of this single message, but that's a new message entirely, then if I use CBC, then I should have at this point picked a new IV prime, and XOR it with M3. But what if I wanted to save on bandwidth, and I just kept the last block as of the ciphertext I outputted as the IV that I will use for the next message? This circuitry seems to basically be designed in this way. So maybe I could do this. Also, in some applications, it's not clear where the message ends. Think of encrypting a buffer. You are getting stuff on the buffer. It's a stream. Basically, a message is a stream. So what do you do with the stream? You start encrypting it. You treat it as a single message. You start encrypting it. Then a stream ended. Do you wait with sending the ciphertext? No, you would like to just send this part of the ciphertext, and then you wait for the next messages in the buffer, next blocks in the buffer, and you continue encrypting them. This is equivalent, right? It's the same idea. If your message is a stream, and if you release block of ciphertext before the message ends, then you're effectively implementing a new encryption scheme which is stateful and reuses IV for the next message as the last block of the cipher of the previous message. Because this distinction happens on the application level between, like, what's the message? Is it a stream? Is it not? Can you pre-send part of your ciphertext before you're done? So it happened in applications, and there is an attack against this. So unclear message boundaries led to attacks, because see what happens when in CBC attacker can predict the IV used by the challenger on the next message, and this is exactly what happens in these streaming applications, right? Sorry, an attacker, if this is a streaming application, is the next element of the stream already determined, or are they subject to adversarial control and interference? Let's say what you're encrypting is HTTP traffic. Perhaps the messages that come after are functions of something else in the system. An adversary can influence them. They're effectively new messages. And this is a case of adversary predicting IV, because the IV that is effectively used here will be the last block of the ciphertext. And of course, adversary has seen that. So here is a type of attack that is possible. Suppose that an adversary can predict the IV for the next message, given the ciphertext of a previous message. So here is an attack, CPA attack. He sends an encryption of a, say, okay, let me test, I want to encrypt a 0, an all 0 string. Okay, the challenger picks an IV and run a CBC mode encryption of this plain text. What is it? Well, the CBC circuitry says, take a plain text, and the plain text is a single block. X is the space of blocks, right? X is the domain of the block cipher. So he takes this block and he XORs it with an IV, and that's what he encrypts. Now, let's say that the attacker predicted the next IV, and he sends 2 challenge messages. This was a CPA query, the chosen plain text. Adversary knew the plain text he wants to see an encryption of, and this is a challenge query. There's a pair, M0 and M1, of 2 different messages, and adversary will be able to distinguish whether this or that was encrypted and break security, right? The 2 messages are like this. This one is a concatenation of this predicted IV with the IV operated here that the adversary has seen because it's a ciphertext. M1 is any other message. So in the case you encrypt M1, what do you see as a ciphertext? You see an IV, which we assume the adversary predicted, and a block cipher applies to M1 masked with this IV, right? Because that's the way CBC encrypts. Both M0 and M1 are single blocks. What do we see here? We see an encryption EK of M0 masked with IV, but M0 is an IV XORed IV1, therefore IV and IV will cancel, and it will be just EK of IV1, which we have seen here, right? So therefore, attacker can distinguish this case from this case because he compares this block, the second block of the ciphertext, which is either this or that, to the second block of this ciphertext. And if there is a collision, he knows that the encryption was of M0. And if there is no collision, the encryption is of M1, right? So he takes the second block, I indexed the blocks, the first block was at 0, right? So this is the block number 1, which is this one in C, and the same block in C1, right? And basically it was a bug in the way SSL, so this bug was used in the SSL that effectively the previous cipher block was an IV for the next, and also it would come up in if you try to do streaming with a CBC, and and basically was not careful about message boundaries. So it's a curious. Any questions on this attack? Okay, I think it's a good coin. You can ask. Okay, sorry, I will ask questions instead of you. It's a little bit obscure attack. Who cares if IV XOR IV1? Is how common is it that the message is a XOR between two IVs? The thing is that, yeah, this is an example. Perhaps you can generalize this. Perhaps you can, of course you can, right? This is an arbitrary thing. Why 0? Perhaps some other plaintext blocks can be used. What if there is many of them to choose from? What other patterns of XOR would lead to the same attack? Given that you have observed many other chosen plaintext attack queries. Bruno is asking that the CBC attack was fixed in 2006. I forget when it was discovered. The thing is that with this SSL, with these standards, is that sometimes practitioners are not convinced that these attacks correspond to really attacks, that they're not like disaster attacks. Because even if you have polynomially many choices of messages, your messages have here, basically what you will do, you will be able to distinguish XOR of any of such with the IV. The chances that any such XOR encodes into some message of value might still be low in practical applications, except that it's very application dependent. So, what's a meaningless message in one application might be a meaningful message in another. This software is all over the place, right? Like it's any server implements the stuff. You have different different variants, different vendors. It is hard to update. And it is sometimes not clear whether, to everybody that the update is really necessary. There's other bugs in the software, that you need to fix. And there is also, that when you fix this bug, that you don't create any new ones, and on and on and on. So yeah, so that's why it takes time. You can, if you compare this analysis of CBC and randomized counter mode, basically everything is worse for CBC. First, it must require the circuitry of the cipher to be invertible. In truth, if we start with the block cipher, it is invertible. It is designed to be invertible. On the other hand, Rand-CTR could use a simpler circuitry. So it is potentially beneficial, even though it's not in practice used. This is not, nobody takes advantage of this gap. Randomized counter model had parallel processing both in encryption and decryption, CBC only in decryption. And the bounds were worse for CBC. So basically, randomized counter model is simpler, is better in every way. CBC was first, And I think that it was preferred by many because it looked more complicated, because it looked like more something, you know, this circuitry looks like there's more mixing between messages, they influence one another, and the IV is and um, and this circuitry seems somehow too simple. The messages don't influence one another. This is taken on consecutive values. There seems to be less crypto magic happening, and yet it gives you a more secure construction in many more secure, more efficient than the complex Y. And also there is no such attack against randomized counter mode. Wait a second. Is there? No, actually there would be. Sorry. Yeah, there would be. There would be the same type of attack, I think. But on the other hand, it shouldn't be entirely dismissed, because they also use slightly. So here is also if a cipher is instead of a PRF, it's a weak PRF. That means that instead adversary asking for that adversary can arbitrarily ask for any points x1, x2, x3, and see the cipher operated on these points. Yeah. Then these constructions only use weak PRF security, basically, which means that the cipher is always asked on a random point. Adversary cannot arbitrarily choose these inputs. No matter how he chooses messages, they are going to be randomized, and this one will be randomized, etc. But I wanted to say that in here, the cipher is being queried on predictable values, but that's actually not true. Again, this is a random value that adversary has no control of. The only thing is that the cipher will be asked in these two executions. The input of the cipher differ by only 1 bit. And so therefore, you cannot argue from weak PRF security. Because if the only thing you knew, that if you ask it on completely randomly sampled points, then the outputs are as if random. Then this wouldn't have worked for you, because here it is not asked on uniform points. It's asked on, yes, the starting point was uniform, but the next L of them are just the starting point incremented by constants, 1, 2, 3, 4, etc. So the advantage of PRF of the randomized counter mode, do come at the cost of actually the assumptions about the cipher in a CBS case could be weakened, and they cannot be weakened for the randomized counter mode. That's, I think, all I had, and that's good because we are basically right on time. Tell me if you have questions. Okay. So thank you for comments on the chat. And oh, Xiaochen has asked, what if we replace chosen IP? Oh, you asked it a while ago. Sorry. What if you replace the chosen IP after that many blocks? Yeah. Xiaochen, do you still have this question? Because I'm not sure I understand it. And you had it a while ago, so. Okay, I'll stop recording.